Good morning, students. Today we will see some of the properties of viscous fluid, and one of them is the rate of change of the circulation. So now, if gamma be the circulation around a closed curve moving with the fluid, okay, and if q bar be the velocity of the fluid at any time t, then the equation 1 gives the definition of the circulation around that closed curve C. Okay. So if q bar is the velocity of the fluid at any time t, so its mathematical definition is q bar is ui plus vj plus wk, where I, j, k are unit vector, and r bar is the position vector of the point p at which the velocity of the fluid is q bar. Now, if we simply take the total rate of change of that circulation gamma, then you see in the integrand of equation 1, there are two types of function. One is your q bar and one is your dr bar. So if you differentiate first time, that is if you differentiate u, then you are getting the total rate of change of u is du dt into dx plus dv dt into dy plus dw dt into dz, plus the second part u into ddt of dx. Now the ddt of dx, it is given as, and after differentiation it is du. So you are getting u du u plus v, and when you find the total rate of change of dy, so you are getting dv as the same procedure of this part. Similarly, when you differentiate or when you find the total rate of change of dz, so you are getting dw. Now you can easily integrate this part. So this will be u square by 2 v square by 2 plus w square by 2. So, and this is a closed circuit. Now what will happen to the closed circuit? So if it is a closed curve, then its starting point, that is the point from which the curve starts, it will come back to the same point. That is, the starting point and end point is same. So if the starting point and end point are same, means for a definite integral, the upper limit and the lower limit will be same, and that is equal to 0, provided there is another condition behind that is it should be single valued function, that is at the starting point and the end point, that is at a particular point the function have only one values. Okay, so you can say that for the first integral also the value may be 0. Yeah, it may be 0, but we don't know what is the outcome, whether it is single valued or not, we don't know. So that's why we cannot write the value of the first integration as 0, because till now we didn't solve that equation. Now for the first integral we had that part ddt of q bar. Now the expression of ddt of q bar comes from the Navier-Stokes equation. So this is the expression of the ddt of q. Now if the external force system is conservative, so if it is a conservative, then we can write that the vector is equal to gradient of some potential function, and the minus sign indicates that in the beginning the potential is higher, as the time goes or as the point goes, the potential is a decreasing function. And there is another identity which we will use in our discussion, that the dot product between del A and dr vector is equal to d of A. So using this identity, first we substitute the value of ddt of q bar as f bar, and f bar from your conservative system of forces, del p by rho, this. Now if you take this identity, that is del A dot dr bar as d of A, in your first two expression we will get the in differentiation form. And from the third part, as nu is a constant, so we have written nu outside the integral sign, and the operator del square also written outside the integral sign, because by the assumption that differentiation under integral sign comes. Now as the first part is integrable, so we have integrated it again the closed circuit, so its value will be 0. So ultimately what we have obtained, the rate of change of circulation as this part, nu times del square of tau. Now if nu is 0, means if the fluid is inviscid fluid, then what will happen, ddt of gamma will be 0, that is gamma is constant. So this is your first article. Now we come to the second article. This is the dissipation of energy. Now, what is the dissipation of energy? Dissipation of energy come to the point that if there is a viscosity, then its momentum or velocity will reduce. Now, if velocity is reducing, its kinetic energy will be reduced, or its kinetic energy will be lesser. Now, we had one principle that conservation of energy means the sum of all energies must be constant. So, similarly, if the kinetic energy is reducing, there must be an increment of some another kind of energy. Now, this is called the dissipation of energy. That is, one energy is reducing side by side, another energy will increase. And this dissipation of energy appear due to the viscosity or internal friction. Now, we will see what is the mathematical expression of that dissipation of energy. So if tau be the kinetic energy of a fluid moving with the velocity q bar at time t with constant density, mainly we are dealing with the incompressible fluid. So the rate of change of kinetic energy, so ddt of t, where t is the kinetic energy. So now using the differentiation under integral sign, there are two functions. One is rho dB. So rho dB is mass. So when you differentiate first function, you are getting 0. Why? Because the mass is conserved. And now we are differentiating second term. Now q square can be written as q bar dot q bar. So after differentiation, we are getting this expression. So 2.5 will cancel. So rho dB q bar. Same by Navier-Stokes equation. We have substituted the value of f bar 1 by rho del p. Knew this. Now this is the first expression, second expression, third expression from this one. And mu equal to nu into. Now, what is that? Velocity into force. Okay. Now, velocity into force can be written as force into. Now, velocity is distance by time. So, velocity is force is nothing but force into distance divided by time. Now, what is force into distance? This is work done. So, velocity is into force is nothing but work done per unit time. Okay. So the first part, this is represents the work done per unit time by the external force. Now for the second part, we use one identity. Yes, this is the identity we are using. And in that identity, the third part is 0. Why? Because of the incompressible fluid. That is from continuity equation. So the second term can be written as in this form. And now by Gauss divergence theorem, this part can be written as pq bar dot nk. Now this indicates that the work done by the pressure force per unit time. So till now we have obtained the two work dones, and this part is the dissipation of energy. Yeah. So if d is the dissipation of energy, and it is defined as in this form. Okay. So it is given in the minus sign because the rate of change of energy, the first two parts are producing and the second dissipation. It is means kinetic energy is reducing. So that's why minus sign is there. Now first identity, this is one of the identity star. Same, its value will be 0 because of the continuity equation. So you can verify it. So we are using this identity in equation 2. So we have obtained the equation 3. There is one more identity. Yeah, this identity. So from this we have finding the value of the right hand side of 3. So using 3 and 4 in equation 2, finally we have obtained our dissipation of energy in this form, and by using the Gauss divergence theorem here, where del is replaced by n cap, the volume integral is replaced by surface integral, and the other conditions for using the Gauss divergence theorem is already verified, that is the system is continuous and the partial derivatives exist. Now this is the third article of the viscous fluid, that is the vorticity equation. So simple one. So it also comes from the Navier-Stokes equation. And this is the ddt, that is the total rate of change. It has two parts. One is that the local derivative and one is that the convective derivative. So now we are replacing this convective derivative by the use of one identity. Yeah, this is the identity and this is the convective derivative part. So we are using the equation 2 in equation 1, that is we are replacing the convective derivative part. So this is the case. Yeah. Now what we'll do, we will take the curl on both sides and we use another identity, that the curl of grade of scalar equal to 0. And we are replacing our f bar as this for conservative system of external forces. So if you take the curl on this side, what will get? Curl of grade of scalar. So this part will 0. Curl of grade of scalar, this will be 0. Curl of grade of scalar, this will be 0. The non-zero part will be del t of curl q, because q bar is a vector. So when curl is operated, so it will be operated on q bar, not del t, because it is a scalar. So del t of curl q. Now for this part we are taking curl, and on the last part. Now this part, this is a for this part we are using another vector identity like this one. Yeah, this is the vector identity. So we are using this vector identity from this part, saying you can verify it. Okay. Now in that vector identity, this is 0 because of that continuity equation. Divergence of velocity vector is 0. So whenever the fluid is incompressible, you always remember that the divergence of velocity vector must be 0. So that's why we have cancelled in all our cases, because mainly we deal with the incompressible fluid. This term is 0 because of that identity, that is the divergence of curl of q bar is 0. So these two terms are 0. Now del t, local derivative. With this local derivative, we are bringing this term because this is giving us the convective derivative. Okay, and the remaining term is minus. So we have taken this term in the right hand side. So local plus convective is this. So this is also known as the vorticity equation. So till now, these are the three important properties of viscous fluid. In our next class, we will discuss the last topic of the third unit, that is the unsteady flow over a flat plate. So thank you all.